Hello everyone. This lesson is an introduction to the normal distribution. Now the normal distribution is a probability density function, just like we've been studying. But this one's rather more common than most because there are a great deal of natural phenomena where if we were to take a series of measurements for a very large sample of the population, then the measurements would conform to this sort of distribution. Now the formula for this curve, this green curve here, otherwise known as the bell curve or the normal curve, the formula is given here. Now thankfully you don't need to memorise this. This is such a common distribution that the formula here is built into your calculators. So let me just run through this a little bit. We know that 2, pi and e are constants. X is our variable along the horizontal axis, that's our continuous variable, and px is our probability density function on the y-axis. Sigma, as we've seen, is the standard deviation, and mu, there's mu sitting up there, that's the mean. Now if we were to change a few of these parameters, I've set currently the mean is 0. You'll notice that the peak of the distribution happens to be on 0. This is a symmetrical distribution. The curve has the same shape on both sides of the mean. And I've got standard deviation sigma of 2. Now, I also have a point here that I can drag along the curve to different coordinates. And I can see here that if I were to substitute 4 for x into this equation with the given values of mean and sigma, then the probability density function would calculate out to be a very small number, 0.03. The peak value, if I was to substitute the value of the mean into this, the peak value is 0.2. Now, let's see how your graphing calculator will do the same sort of thing. If we go into the statistics app, distributions, F5, normal distribution this time, F1, and a normal probability density function. Here it is. Now I've set this, let's set this up to be the same. I'll need a standard deviation of 2 to match what I've got on my screen. I'll need a mean of 0 to match what I've got on my screen. And currently I have my x coordinate of this point set to 0. So then I run down here and I press draw. It draws me the same function. It tells me the value of the function. It doesn't put a point like I've got, but this value p represents the value of p, and x is 0, so p0 is 0.199. Very close to 0.2. Mine's rounded off a bit on GeoGebra. The calculator is giving me lots of significant figures. So that's how your calculator can show you what we've got here. Now, we can always change the mean. If I make the mean go up to 5, notice that now the peak of the distribution is here above 5, but it still has the same symmetrical shape around this point. Now, if I was to slide up here to 0.5, there it is, and yes, now that I substitute 5 into this with a new value for the mean, I still get the same value for the function. Let's see what effect the standard deviation has. Let's make the standard deviation a little bit smaller. The standard deviation of 1. Notice that the mean is still at 5, the peak value is still at 5, but the peak is higher, and the distribution is, the width of the distribution is less. So the standard deviation, measures the spread of the data. So a small standard deviation means that the data is bunched up. A large standard deviation would mean that the data is spread out. It's still a bell-shaped curve. It still has the mean, the peak value at 5, the way we said. Now I could change the mean, and I could change the standard deviation to any combination I like. I'm not going to get standard deviations less equal to 0. A 0 standard deviation would just be a perfectly straight line, a thin line going up forever. So I've set that to be a lower of 0.1. And of course standard deviation can go up as high as you like. Now let's have something like 1.5, and that's good. Mean of 5, standard deviation 1.5. Now you're probably wondering what these other values here, A and B, are. As with any probability density function, we can find the probability of events lying between two values, an upper and lower value A and B, by integrating the function. Now don't worry, you don't have to integrate this function. You don't even have to remember this function. So let's make this go up to 5 here, and this one's at -5, but by the time we get to -5 down here, the density function would be very, very, very low. So it's effectively, look, it approaches asymptotically, but it's effectively run out of anything by the time it gets to there. So what is, just put that one off to the side, what is this area from the peak all the way down to the left-hand tail? It's 0.5. How interesting. Now, I wonder if I was to bring this slider in a little bit and stop at 3.5. There we are. So remember, the mid value here represents the mean. The standard deviation is 1.5. So I've gone 1.5 lower than the mean. It's 0.34. 34% of the area under this curve is in that space. I made a mistake by putting mu at 5 there, didn't I? Let's bring the mean back to 1. That's better. Now I'll have a better chance of doing this. Let's put the B value at 1, and A is 1 as 1. Whoops. Should be minus 0.5. There we are. And so that's the same idea, 34%. What if I take the upper boundary here from 1 up to 2.5? This represents the mean minus 1 standard deviation here, and this represents the mean plus 1 standard deviation here. This is 68%, or roughly 2/3 of the population, or roughly 2/3 of the data points in our large sample would lie between the plus or minus 1 standard deviation from the mean. Now, how do we use our graphing calculator to tell us this sort of information? Well, let's just pop back to here. So we go into distributions, we go to normal distribution, and this time we are looking to calculate the area underneath, so we need a cumulative distribution, the normal cumulative distribution. Now my lower limit this time, lower and upper here, refer to the lower and upper limits of this integral. So my lower limit is -0.5, my upper limit is 2.5. My sigma is 1.5, and the mean is 1. I can draw this, so it draws me the graph. Now, you'll notice that the drawing on the calculator looks slightly different to this one. It automatically rescales, it centres from the mean. So it puts a line down through the midpoint, and it doesn't go in normal steps. This step of +1, that's not a step of 1 on our scale. It's 1 standard deviation higher than the mean. We call it a z-score. And the negative side of the scale is a z-score of -1 because I went 1 standard deviation lower than the mean. It still gives me the same area, 0.68, or 68% roughly. Now, that's a nice little introduction, I hope, for the normal curve. The graphic calculator is all you'll have with you on exams, so you should become very familiar with this distribution key, normal, and the difference between which each of these functions give. The GeoGebra worksheet that I made here, this is for demonstration purposes only. You won't have access to that in exams. But of course, you can build one of these for yourself on your own computer and play around with it to learn about this function. Thanks for watching.